Hi everyone, I'm Ben Watson, a hydraulic modeler at Jacobs. I've been working in the water and environment industry for about 4.5 years. And as part of my role, I work on hydraulic modeling projects on a daily basis using Flood Modeler for a range of clients, both within the UK and abroad. And today I'm going to provide an introduction to 1D urban drainage modeling and introduce Flood Modeler's 1D urban solver. So I'll just go through the agenda of the presentation. I'll start with the basics, the what and why of urban drainage modeling. I'll then move on to talk about how 1D urban drainage modeling can be used as part of an integrated approach for catchment modeling. I'll cover the 1D urban solver, the data required to build a 1D urban model within Flood Modeler, and then finally a quick live demo of Flood Modeler's 1D urban solver, and there'll be some time at the end for Q&A. And I'd just like to highlight that today's webinar will focus on the 1D urban and 2D solvers within Flood Modeler. However, the 1D river solver is also available and can be dynamically linked to the 1D urban and 2D solvers using an integrated catchment modeling approach that I'll come onto within this webinar. So before we get into the details about Flood Modeler's 1D urban solver, let's cover 1D urban drainage modeling more generally. Urban drainage network modeling in its simplest form is the representation of hydraulics within the subsurface urban drainage network. This involves modeling the complex network of pipes, manholes and structures such as pumps and tanks as 1D model components. Similarly to 1D river modeling, flow conveyance throughout the network is then simulated once inflow and outflow boundaries have been added. Within urban areas, this allows detailed understanding of key issues in the network, such as pipe capacity, points of flooding from manhole surcharge, and discharge via outfalls. The user could then go on to option modeling to improve the network, such as pipe upsizing, additional storage, or the addition of new branches. We can then link the 1D urban network to the surface, such as at manholes, and then represent both surface and subsurface flows and the interaction between the two to get a better idea of runoff routing and key flood mechanisms related to the urban network. And I'll come on to that in a second, but all of this capability is now available using Flood Modeler's 1D urban solver. So 1D urban drainage modeling obviously has benefits as a standalone modeling approach. However, a key benefit to representing the 1D urban drainage network within your model is the ability to conduct integrated catchment modeling. Integrated catchment modeling refers to the detailed modeling of the catchment and the complex interactions between the drainage network, river channel, and the urban area or floodplain. So to illustrate the importance of integrated catchment modeling, I've shown two images. The left image shows a typical 1D, 2D fluvial model where runoff from the urban area has been modeled using a subcatchment rainfall runoff model that's been discharged to a 1D river node at the outflow point of the catchment. The issue here is that the subcatchment is highly urbanized and therefore a number of assumptions have had to be made regarding land cover type and area, drainage network capacity, and the point of outfall into the channel. Also, flooding can only be generated via out of bank flow from the channel into the urban area. The image on the right-hand side then shows what can be achieved with an integrated catchment model. So the subcatchment inflow has been removed and the 2D model domain extended. Inflow to the subcatchment has been added as direct rainfall onto the 2D grid, shown in this blue hatched area. And the drainage network has been explicitly represented using a 1D urban model domain. Rainfall runoff routing has therefore been accounted for in the 2D domain, and the 1D urban, 1D river, and 2D components are dynamically linked. This model allows the user to identify pluvial flooding mechanisms such as surface water flow paths due to rainfall accumulation on the surface, flooding due to the surcharging of manholes within the network, and the usual out-of-bank flooding from the river channel, giving the user a more detailed overall picture of flooding mechanisms within the urban area. And just to show a bit more detail on what those links look like in Flood Modeler, so the 1D urban network is dynamically linked to the 2D domain using 1D urban 2D linking at manholes. The outfall of the drainage network has been dynamically linked to the 1D river domain using 1D urban 1D river linking. And the 1D river domain has been dynamically linked to the 2D using 1D 2D link lines along the channel bank tops. And this integrated modeling approach combines the benefits of 1D urban, 1D river, and 2D models. This means we can take all of the good parts of 1D river and 1D urban models, such as the ability to include a detailed representation of the river channel or network, a detailed representation of hydraulic structures, and the ability to model complex operational control features. And we can combine them with all of the benefits provided by 2D modeling, such as having the ability to model multiple flow routes across the floodplain, identify flooding to properties and receptors, and it allows the production of 2D flood maps and grids to inform economic appraisals. And by combining these approaches into an integrated model, we end up with a model that has a wide range of applications, such as the modeling of fluvial flood mechanisms. So we could use a fully linked model to improve understanding of the baseline flood risk in an area, identify the onset of flooding, and key locations where flooding originates from. We might already be aware of fluvial flooding due to overtopping of a riverbank, but integrated modeling may identify further flooding from the drainage network, for example, due to the outfall being inhibited by high water level within the channel. Or we may be interested in modeling an engineering solution, such as linear defences, and we want to firstly make sure that the defences are not going to prevent surface water flow paths from entering the channel. And with the 1D urban solver, this can now be achieved all in one place within Flood Modeler through the use of our multiple solvers. So the 1D river solver for modeling river channel networks, the 1D urban solver for drainage networks, and the 2D solver for surface water and overland flow. And it's important to note that each of these links can be created within Flood Modeler using the automated linking tools, which automate the process and make linking much more efficient. So I'll give a quick summary of the 1D urban solver within Flood Modeler and its capabilities. The 1D urban solver is a fully hydrodynamic flow and level simulator for closed, open, and hydrological systems, meaning the software will simulate time-varying hydraulic results throughout the network, such as flow and water level, and throughout the period of the simulation. The 1D urban solver is derived from the US EPA's SWIM software. Anyone that's familiar with SWIM will be able to pick up the 1D urban solver quickly and efficiently. The SWIM engine is a widely used industry standard software that's robust and trusted internationally. Alternatively, the 1D urban solver has been developed to be intuitive and easy to use. So anyone new to 1D drainage network modeling will be able to pick it up quickly, particularly through the use of our Getting Started guides and training courses. The 1D urban solver allows detailed modeling of single, looped, or branch drainage networks. So single would be when there's a linear reach of pipe with no additional reaches joining. Branched would be when there's multiple reaches that connect together at junctions. And looped would be when there's a complex network of pipes that are interconnected at multiple locations throughout the urban area. And there are also multiple options for the user to specify the calculation specifications, such as which equation to be used for calculating pressurized flow within the network. The 1D urban solver was recently benchmarked against other available modeling software with drainage network modeling capabilities, finding that Flood Modeler was up to 49% faster, providing results that were in close comparison with the other software. And importantly, existing 1D drainage network models, such as those within InfoWorks ICM, can be quickly converted into Fluid Modeler using our efficient conversion process provided in the step-by-step guide on the Fluid Modeler website. So I'll shortly be going to Fluid Modeler to give a demo of the 1D Urban Solver and how to build and simulate 1D urban models. Before that, I'd just like to provide a summary of the useful data that should be gathered to aid in building a 1D urban model. So firstly, inflows to the 1D urban model are required and can be applied in various ways. Direct rainfall can be applied directly to the 2D model domain, and a linked 1D urban 2D approach can be used to route flow into the 1D urban network. If explicit modeling of the 2D domain isn't needed, then flow can be directly applied to the 1D urban network at nodes using a simple flow time series, or a subcatchment approach with an attached rain gauge can be applied, such as the configuration shown on the right-hand side there. Secondly, and most importantly, details of the sewer network are required. So preferably as GIS points and polylines that can be easily imported into the integrated GIS user interface of Fluid Modeler and used to digitize the 1D urban network. A terrain model, such as LiDAR DTM, which is readily available for the entirety of England from the DEFRA web service, can be used in Fluid Modeler to identify the ground elevations at manholes and therefore specify the elevation at which manholes begin to cause flooding. Or LiDAR DTM can be used in the 2D solver to define the local topography in order to simulate overland flow propagation. Land use information, such as OS master map, can be used to define 2D hydraulic roughness coefficients within the 2D solver. This can be used to improve the accuracy of overland flow estimation by applying land use specific roughness values within the 2D domain. And finally, a downstream boundary or downstream boundary information is required to apply a downstream boundary condition to the 1D urban network. This can be in the form of a water level time series, so that could be fluvial or tidal, a fixed water level, or the user can specify a dynamic link to the 1D river network via 1D urban, 1D river linking. Alternatively, if the downstream boundary is of limited interest, the user can specify a free flow or normal depth boundary at the downstream boundary condition. Okay, so I'll move over to Fluid Modeler now to provide a demonstration on how to put that information together and build a 1D urban model. Okay, so I'm starting here with a blank Fluid Modeler workspace, and I've already added in the background mapping. So I want to begin by opening up an existing 1D urban network, which is called an INP file. So in the top toolbar here, I'll go to Load Urban Network. I'm just going to grab my top one there. So you can see when it opens up, if I just drag that out, the INP file actually opens twice. And that's because the INP file houses both the actual model network and the simulation. So you can see that the network is made up of a series of junction nodes, conduit links, subcatchments providing inflows to the model, and a rain gauge that provides rainfall inputs to the subcatchments. However, hopefully you can tell at the downstream end, the network is incomplete and so needs editing. We want the network to end at the river channel that's shown here on the background mapping. So we're just going to add a few units just to complete the network there. So using the 1D Urban Build toolbar, I'll start by adding a junction. And then an outfall at the river channel. So firstly, we want to specify some values in there. So we'll start with the junction. And I'm going to leave everything as default apart from the invert elevation. So I'll just put some numbers in there. And same with the outfall. So again, just double click, specify the elevation you want. On the outfall unit, we need to define our downstream boundary condition. So using the type drop down, I'm just going to select normal. And we'll save the urban network. Then what we want to do is add links between the new nodes. So firstly, if we go to model defaults, we can see in here the default settings for adding new items. So we could have done this for the nodes and specified default node max depths, node ponded area, node invert levels even, but we just added the invert levels manually. But I'm going to keep the default circular, and we can see in here that the default's set up to a 0.6 meter diameter circular pipe and a roughness of 0.035. We'll leave that as it is. I'm just going to add links between these nodes. So we select the add link tool. That'll bring up the add link box here. And then you can quickly just select the node you want to link together. So I want to go from there to there, and you can see it populates the box, add link, and then there to there, again, add link, close, and save the network. Once we've completed the network, we then want to run a simulation. So very simply, we go over to the 1D urban simulation, right click and click run. That'll bring up the kind of run simulation box that users of Fluid Modeler are familiar with. It is a very, very quick simulation, but we're not going to wait for that to finish. So I'll just close that. And I'm going to bring in a simulation that's already complete. You can see this is the same model. It's just been simulated already. And there's a few different results you can look at in a very similar way to 1D river models. So you may want to look at water level within a node. So you simply select the node, go to the results toolbar, go for time series. So here you can select multiple nodes, and you can see there's a few different options for types of results. I want to look at water level, so I'm going to go for node head, turn off flow. And we can click through all nodes to see water level within the node. Alternatively, you could plot a few different nodes at the same time. Within a link, looking at results is very similar. So maybe we want to look at these two links. And again, we'll go to time series. And we're going to have a look at link flow. So you can see here, we're showing the flow through those two different links. And then the last example of results I want to show is a long section. So if you want to plot a long section of the entire reach, you can just select one link at the top, click long section, and you can see we can animate the water level within the network throughout the simulation. Maybe we just want to look at a specific reach. So if that's the case, you can select multiple links and again, go to long section, and you can animate water level within that reach of network. Okay, so we've got a 1D urban standalone model that provides results within the subsurface network, but now we're going to set up a 1D urban model linked to the 2D domain or urban area. So firstly, I'm going to load in a slightly different 1D urban network. So this is pretty much the same model. The only difference is that the subcatchments have been removed, and that's because we're going to account for the urban area within the 2D domain. So instead, we've added inflows directly to the 1D urban nodes, and you can view that by looking at the flow time series applied at the junction units. Okay, so I'm going to load in an existing 2D simulation. So we go over to the simulations, right click and add item. And then if I go into my 2D folder and select an existing XML file, and we'll click yes to bring in the GIS data. So you can see the 2D simulation is very simple. We've got a digital elevation model covering our area, and we've got a very simple active area as well, defining the 2D domain. All that's missing then is the link between the 1D urban and the 2D model domains. And we're going to do that using the quick 1D urban 2D linking tools. So I'll select that tool, and you can see that I'll bring up this table on the right-hand side. Very simply, you just want to select all nodes that you want to link to the 2D. So I want to grab everything apart from the outfall. You can see the links are set up as Q-type links, so flow links. There is also a where link for the junction nodes, but we won't come onto that now. Right click once you've selected and create 2D linking for selected nodes. That'll bring up the 2D urban linking box, and we want to create a new 2D linking shapefile. So we'll call this 1D junction links, and OK. And if I just zoom in on one of our junctions, you can see that there's a cell selected around each of the junctions, defining the link between the 1D urban and 2D domains. Okay, so we've created our link. We now want to set up the link simulation and run it. So we go to the simulation that I've already loaded in, right click and open. That'll bring up the 2D simulation file that hopefully users are familiar with. We've got our time steps. We're running on a CPU solver. We've got our digital elevation model for a single domain and an active area. What we want to do is link to the urban domain. We could link to a 1D river model, but we don't have a 1D river model in this case, so we're going to select the second option. And you can see that brings up the 1D urban links tab. So we'll go to there, and there's two things it's asking us for. So the first thing is the IMP file. So you just drag that in. So that's your 1D urban file. And then the second thing is your 1D 2D link shape file that we've just created. I'm just going to change a couple of the defaults just to be specific for this model. Click save and run. And again, that'll bring up the simulation window for the 2D and the 1D urban. So again, I'm just going to close that down and open a simulation that's already finished so we can have a look at some results. So I don't need to load in the 2D GIS files for this because it's the same model. And we'll go to the simulation that we've loaded, right click and view result. And then you've got a choice of layers that you can bring in. So I want to look at depth and velocity. So I'm going to turn the others off, and I'm going to select all time steps. And you can see that brings in the maximum depths in the 2D domain. If we go to the time step tab, we can play through a simulation of the 2D results and watch the flow path propagate throughout the simulation across the 2D domain. Alternatively, scroll down to the bottom and go back to the max values. The 1D urban results are then the same as we looked at before, but obviously you've got a linked simulation. So again, we could select a few nodes. So if we go for those two, go to results and time series. And again, I'm going to look at node head to see the water level. So that's the water level in those two nodes. Or we may want to look at a long section again. So I'm going to just select the upstream one to give me the whole network, long section. And we can play the simulation of the long section. And we can see pretty quickly that the junctions and the kind of manholes that are surcharging correspond really nicely with the areas where we've got flooding in 2D. Okay, so just some kind of key stats on this model. The model has just over 5,000 2D active cells, and I'm running the model with the default ADI solver in CPU, and it completes in 8 seconds. Obviously, we don't need to be using the GPU in this instance because it runs so quickly, but when using the TVD solver in GPU, the run would complete in approximately half the time. And then finally, I'd just like to highlight the multi-edit tool. So when we were making edits to the network, I was double-clicking on the nodes and manually entering values. But you could actually use the multi-edit view tool up here in the 1D Urban Build tab. And that would allow us to make edits to all junctions, links, outfalls in one place. So we can make manual changes that would cover everything. So for example, we want to make a change to the invert elevation, change everything by a certain amount, or the ponded area, or perhaps we want to change the roughness of all pipes. You could do that all in one place. Okay, so just to summarize, the 1D Urban Solver is developed to be intuitive and easy to use. 1D Urban networks can be visualized, built, and edited within the same Fluid Modeler GIS user interface that users are familiar with. The 1D Urban Solver is proven to be fast, performing up to 49% faster when compared to other benchmarked software. And finally, the 1D Urban Solver allows integrated modeling all within Fluid Modeler through dynamic linking between 1D Urban, 1D River, and the 2D Solver.